And I've been a KNIME user for 3 or 4 years. I use it as the software tool for courses I teach with UC Irvine in their Predictive Analytics Certificate program. I also use it for the text mining course I teach through the UCSC's Data Mining Certificate program. And it occurred because when I was searching for the open source software that was available and wanted to find something that was easy to use and could accomplish the kinds of things I wanted to accomplish in my teaching, KNIME was really easy. You know, to be honest, the rule of thumb I use is I load up the data set I know, and if in an hour I can build a model using the data prep that I want to do and get something useful out, then it's easy to use, and I was able to do that with KNIME. But this webinar is not about those specific aspects of KNIME. It's about strategies for predictive modeling, and hopefully I'll be able to get through a good part of this, maybe not through the whole thing, and if I can't get through everything, maybe we can do a part 2 sometime. But want to talk about several strategies, just high-level strategies for building predictive models, and these are the 4 areas I want to talk about. One, we want to know what we're doing, so I want to define what we mean by predictive analytics. The second step is to have a plan for the project. So when we begin doing our predictive modeling, we want to know what the whole flow of what we'll be doing during the project so that we accomplish each of these steps in the right order. I'm not going to talk about the algorithm today, as enjoyable as that is. I'm going to go past the actual modeling and talk about assessing models the way we use them. And that's a critically important step in any predictive modeling project. And then I'll get a little bit into data prep as we have time to try to do some things for the algorithms that they can't do for themselves. And I'll explain what I mean by that when I get there. So the first thing I want to describe is what is predictive analytics and give some definitions. And one of the definitions that you'll see, excuse me, out there in the world of, in the Wikipedia world is this kind of definition. Describes predictive analytics as statistical analysis that deals with extracting information from data and predicting future trends. And I've color-coded the 2 key ideas, I think, that people think of with predictive analytics. One is statistical analysis, or sometimes people describe it as machine learning or some kind of data analytics. But a lot of predictive analytics, the idea in our minds is predicting future trends, though that's not always the case with predictive analytics, not necessarily trying to predict the future. But that's one of the ideas that is usually incorporated in the definition. The core of predictive analytics relies on capturing relationships between explanatory variables and predicting variables from past occurrences and exploiting it to predict future outcomes, which means that we've got a bucket of columns in our data, a bucket of fields. We're trying to understand how they relate to one another and how they relate, especially to something we're trying to predict. And that something we're trying to predict could be churn, it could be response, it could be the customer lifetime value that we're expecting from an individual customer. It could be fraud, yes or no. All these kinds of things we're trying to find these associations. And what I usually tell people who are new to predictive analytics anyway is predictive analytics does nothing differently than you and I would do on our own if we had enough time to do it. You load your data into Excel and you're looking at individual columns in your data, do scatter plots, run correlations, those kinds of analyses. And when we do those things, we get some insight into what the relationships in the data are. The problem is, most of the time, we don't just have 1 or 2 columns. We've got hundreds, maybe thousands of measures, thousands of attributes that we're trying to assess, and it becomes far too difficult to do in Excel. The only thing I'm going to mention on this slide is the 3rd bullet, which made me laugh when I first read it, by an analyst named Tim Nance, who's paraphrasing a data visualization expert and analytics representative of the Data Warehouse Institute, KDDCup. He says, predictive analytics is data mining rebadged because too many people were claiming to do data mining and weren't. I like the data mining rebadged. Predictive analytics is really nothing new. It's the same kinds of analyses we've been doing for over 2 decades. And Rosario mentioned that I've been doing this for, my bio is old, it says 21 years. I've been doing this since the late 80s, so it's at least 25, 20, probably 27 years now. And it's really the same thing we're doing now that we did back then. The key, though, and what I was trying to get at with my simple explanation of the Excel spreadsheet was predictive analytics is data-driven analysis. We want the data to tell us what's interesting. We want the predictive analytics algorithms to alert us to what the key inputs and input combinations are related to the target variable. And because it's data-driven, it has to be automated. And automation means finding the key input variables, finding the key combinations, and ultimately assessing and telling us which of these predictive models is best. We want as much to be automated as possible so that we are freed up to think at a higher level strategically about what the model means and how we can use the model. Okay, so that's, when I'm describing predictive analytics, that's the kind of thing I'm describing. And just as a shameless plug, briefly, I've got a book that describes all this, and actually everything I'm talking about today, it'll be in the in a book that just came out this week on Applied Predictive Analytics by Wiley. You can look it up if you're interested in it. But it goes through this exact same procedure I'm describing here, and it's a non-mathematical treatment, but a technical but non-mathematical treatment of predictive analytics. Okay, back to the slide deck. So have a plan. So now that we know what we are trying to accomplish with predictive analytics, how do we get there? And one of the frameworks I like to use, and I use this most often, is CRISP-DM. And you can see the term or the phrase data mining in this because it was originally created when data mining was the term du jour for predictive modeling. And so it's short for the cross-industry standard process model for data mining. You can Google search it and find an FTP site on IBM's domain that has the official document, which is about 80 pages. It's useful because it's a description of these 6 stages of the predictive modeling process. It's a well thought out description of this. There's lots of ways people describe this, and most of them are fine. But this one is written in this 80-page document. So these 6 stages that we're going to be talking about: business understanding, data understanding, data preparation, modeling, evaluation, and deployment. And one of the things to note is this is very realistic whenever we build predictive models, is that business understanding feeds into data understanding, or maybe it goes the other way, data understanding feeding into business understanding. But there are feedback loops. Maybe you build your models and they're awful, like most of the time our first models really are awful. Then we go back, we do some new data preparation, create some new variables before we model again. Or we build our models, we evaluate them, and they're awful, and we've got to go back to the beginning and define a new question. I'm going to go into a little more depth on a few of these steps so you have an idea of what we mean. So first of all, business understanding is what we do first to define what the purpose of the modeling project, what those purposes are, what the objectives are. We define the business objectives, and we define them in the language of the business, and we have success criteria in the language of the business. So if I'm building churn models for a customer, we want to, the business objective is to identify customers who churn. And part of that definition is defining what churn means. And part of the definition is defining, once we identify churners, how do we know that we've defined churners that are useful for us operationally? What's the success criteria? Do we need to find 1,000 churners each month? Do we need to define churners that are more than 3 times likely than random, or find half the churners in our data set? Whatever your business is interested in for this business objective is defined here. But then once we do that, we have to translate this business objective into the language of our predictive models. So I mentioned already that we define churn in the language of the business. But once we define churn, we've got to define it in a way where we can populate a column in our data that is the target variable. We have to translate the business idea of churn. So, for example, you may say churn is when a regular customer stops stops behaving in a normal fashion. Okay, now that's obviously way too vague. So then you push the domain expert. So what do we mean by that? What is a regular customer? Oh, well, it's a customer who's visited our website at least 3 times in the past month. Okay, so now we've got a definition, an objective definition. And what does it mean when they leave? Does it mean that they haven't visited again in the next month? Does it mean they haven't visited again in 3 months? Does it mean that they visited but just haven't been on our website for very long during the next month? So those very specific definitions have to be made so that we can populate that target variable in our data mining objectives. And of course, we need our data mining success criteria. Do we assess the models based upon overall accuracy? Do we use lift? Do we use gain? And I'm going to talk about some of those success criteria a little bit later in the webinar. So at this stage, we define everything we're trying to do. Then in data understanding, we're trying to describe what the data we have and explore it so that we can identify problems in the data. Does the data look the way we expect it to? Are there problems with the data? Are there missing values? Is the target variable populated the way we expect? All these questions, which are sometimes the very first time anybody has ever looked at the data in our data set, is when we look at the data for this predictive modeling project. So it's critically important to do the data understanding steps early in the process to uncover all those data problems. And then in data preparation, we're cleaning the data, constructing new data, so we're fixing data problems, missing values, outliers, high cardinality categorical variables, and I'll describe those in a little bit. We create new features in the data, new derived variables, and that could be a webinar unto itself just to describe what we mean by features, what is a good feature, how to go through the process of finding features in a more automated fashion. It's quite in depth. And of course, most of the time when people talk about predictive modeling, they say, well, we spend about 2/3 or 80% or 90% of the time in data preparation. What they really mean is, before you build your first model, you're spending a huge chunk of time cleaning up the data, preparing it so that it's in the right form for you to build your predictive model. Of course, after you do that the first time, you don't want to have to do that again. You don't want to have to do it 3 or 4 times. So once you do that the first time, presumably all those data problems that you fixed, you can reapply that logic again and again, so data preparation is not so big of a deal the next time. And then for modeling, selecting the algorithms we're going to use, do your sampling, train, test, or if you're doing bootstrap sampling or cross-validation, any of these techniques to resample your data. You build the models, and then you assess the models. One of the things you see in the literature sometimes too is there's another technique that SAS has used historically called SEMA, which is also a very nice step-by-step process. So SEMA is really written from the perspective of the analyst. The SEMA stands for sample, explore, modify, model, and assess. And so modify is related to data preparation. Modeling is just like modeling in CRISP-DM. Assess is like evaluation in CRISP-DM. So there's not really an emphasis on the deployment side, and there's not much definition on the business understanding side. So they're both perfectly fine. Okay, so once we have our problems defined, once we've determined the path, how we're going to get there, using a framework like CRISP-DM. And just one last thing about CRISP-DM, that's especially good if you're an analyst and you want to explain to your boss what you do or how you do what you do. Or if you want your boss or a program manager to be able to track the progress you're making on a modeling project, CRISP-DM is a good way to help them do that. But once we do that, when we build our model, I want to talk a little bit about how do we assess the model. The reason why I'm doing this instead of talking about strategies for actually building the models, is there's a lot of science behind how to build models, and you can read about that and take the courses on that. Assessing models is not addressed too much in the open literature. And you'll see some ways people assess models, but there's a couple points I'm going to make in a moment that I think are critically important in describing why we have to be very careful about how we assess the model. So I'm going to talk about a couple of the standard assessment methods, and I'm going to focus just on classification for today, not on continuous value prediction or what some people call regression modeling or estimation modeling. But similar principles apply there as well. I'm going to talk about some of the standard assessment methods and then talk about why these methods matter. Okay, from a classification perspective, what we are doing with assessing the models is something that can be described with this kind of picture. So in this little spreadsheet that I included in the slide, we have control ID as a customer ID. We've got our target variable, which in this case is called target D, and we've got a probability listed here, and a probability that the target equals 1 and the probability equals 0. So let's focus on the probability that the target equals 1. So this is the typical kind of thing we would try to do. This target B is this is from a response model. So we're trying to measure how likely it is that a customer will respond to contact from us. And the top score is 7.3%, the next score is 7.1%, and then we go down and down from there. But notice this is rank ordered from the highest to the lowest because I've sorted this already in here. The way classification models are built and the way they are used and assessed is typically like this. We get a probability out from the algorithm, whether it's logistic regression or a neural network, and then we threshold this probability at some level. So in this case, we say if the probability of the target B equals 1 is greater than some value, like 0.05, above that line, we call our prediction a 1. Otherwise, we call the prediction a 0. Okay? Now, it's important to realize that this is what we're doing, and for a reason I'll mention in just a moment. We'll get there. So when we do that kind of assessment, what we're really getting out of this kind of measure is characterized very nicely with this metric called the confusion matrix, where we have actual class going across the rows and predicted classes going down the columns. So a confusion matrix is just a crosstab of actual versus predicted, where actual, and I'm going to go back a slide, actual is the true value, the actual target D, and the predicted is the 1-0 label after we apply some threshold. Once we get the actual predicted here, we can look at this confusion matrix and we get true negatives and true positives out. So if the prediction was actually a 1 and we predicted a 1, that's called a true positive. If it was actually 0 and it was predicted to be a 0, that's a true negative. And those are green because that's gold for us. Those are the correct decisions. When they're incorrect, they're either false dismissals or false alarms. Actually a 1, predicted to be a 0, or actually a 0 and predicted to be a 1. Because that's the classic way people do assessment of predictive models. Percent correct classification then just sums up the correct divided by all the examples. So it's the true negatives plus true positives divided by everything. So that is what I would call a batch approach to predictive modeling, where we score every record with the same weight. However, there are also rank-ordered approaches. And these rank-ordered approaches can be broken down into 3 main buckets that people use: gains charts, lift charts, and ROC curves. All 3 of these do the exact same thing. If you remember that first spreadsheet that I showed that showed the target prediction rank ordered from high to low, I'll go back there just briefly. After we sort from highest to lowest, gains charts, lift charts, and ROC curves do the exact same thing. You sort and then you measure. So let me show you what a gains chart does. A gains chart sorts from high to low, and that's this x-axis, the population, And then in the y-axis, we count or we measure the percentage of the actual values that we find along the way. So that means at the 20% depth, if we're finding 40% of the actuals, that's a lift of 2 that we see on the right side, because we're twice as likely to find target b equals 1, our target variable, when we sort the data by the metric we chose, which was the model. So that's what gains is trying to measure. And it's saying, are we rank ordering, are we sorting the population better than we would do at random? And the more space there is between this random line and the bow, which is based upon the model, the better the model is. Now, if we had a 7% response rate, or let's say we had a 5% response rate, a perfect model would go from the 0, 0 here, get 100% of the examples at the 5% depth, and then the rest of it would be at 100% because we found everything in the top 5%. So that's the perfect model. And as soon as you get that, you know you did something wrong because none of our models are perfect. And if we found something perfect like that, we're sure that we leaked the target variable into our input variables in some way, shape, or form. Lift is just measuring the gain divided by the random line. So it's a lift of 2 if we're twice as likely to find the target compared to what we find at random. Once you get the idea of sorting, you can measure anything you want based upon this target variable. So, for example, we could measure profit. We could say sort the data from high to low, highest score to lowest score, and then if we know the cost of contact and we know how much revenue or how much gain we expect from trading that contact, we can create a profit chart. This doesn't use the model scores directly. It only uses the model scores to sort. But once we do that, then we can get a chart that looks something like this. So if your organization is building a model and you want to measure return on investment, and that could be a customer analytics application, it could be fraud detection, where there's a cost associated with contacting somebody for investigation, but there's an expected gain from investigating them, you can generate these profit charts. And if that gets closer to your business objective, that's what I'd recommend doing for assessing the models. And again, I'll explain why that is in just a moment. Just one other plug. This article came out recently. If you want to learn more about these kinds of techniques and how individuals use different ways to test the actually predictive models, there's this very interesting article. There's an interview of, it turned out to be me, John Elder, and Carl Rexer. We're interviewed about how we assess models. We describe different things that we do when we're assessing our predictive models. It's very interesting, and I can give Rosaria the URL for this particular article, which I thought was well written. Okay, I'm going to skip this slide and go to the next. This is why it matters, the metric we choose. This spreadsheet shows 2 different metrics that you could use to assess models, and these are 2 different rank-ordered methods. One of the rank-ordered methods is area under the ROC curve, and that's something I didn't talk about here, but that's a common metric someone uses. So in KNIME, I'll show you in just a moment, there is a ROC curve metric that you could use to assess your predictive models. And then there's a top decile response rank. So this is saying what is the decile, the top decile, the top 10% ranking. Which model did the best job at identifying the highest percentage of responders in the top 10% side? Here's the interesting thing. Area under the curve, that's sorted here, highest to lowest area under the curve, and the rank order is in the next column. This column at the far end is the rank ordering based upon the top decile. These are both using rank order techniques, but they're using different rank order techniques. The top performer model is here, and this is the 7th best based upon the top decile rank. In fact, the 20th best based upon area under the curve turns out to be the 2nd best with regard to response rate or ranking. So I'm letting that sink in for you for a moment. The metric matters significantly. In fact, when I've done predictive models in the past. This is one example of a predictive model where I looked at the root mean squared error of a regression model and the area under the curve based upon that regression model, and I created a rank order scatter plot. So these are the rankings, the top 200 models for the area under the curve, and the top 200 models from the root mean squared, and the correlation is almost zero. Different models trade off the errors in different ways. So using the metric which most closely relates to our business objective is important for us to pick out the model that does the best job at addressing our business question. This is why I joke when I'm teaching predictive analytics courses, I've never delivered a model to a customer of mine based upon R squared. I've never delivered a model based upon overall classification accuracy. Now, that's not completely true. I actually have done it before when I've been asked to do it that way. But I only do it on purpose, not because it's the easiest metric we have available to us. So during CRISP-DM, when we define the business objective, one of the things we define are the success criteria. And in the success criteria, we define what metric we're going to use to assess our predictive models. Okay, number 4. Do for the algorithms what they can't do for themselves. And there are some particular issues that occur over and over again with predictive modeling that I wanted to get at here. And that's items like outliers, missing values, and I'm going to talk about high cardinality, what I mean by that. The reason why these steps are important is because data mining and predictive analytics is data-driven. Because it's data-driven, the algorithms use the data to build the models unguided directly by the user, by us, the analyst. For a statistician, a good statistician, the data is, the model is king. The model is where all of that statistician's emphases lie. So you build your regression model and you're carefully tuning the data to make sure it abides by all the assumptions you need for regression modeling. Data mining and predictive analytics is not like that. We usually throw the data at the algorithms and let the algorithms sort out the patterns. But because we're letting the algorithms sort out the patterns, and because algorithms do not have common sense, algorithms believe completely everything that's fed to them. These algorithms look at the data, or they see the data, and if it says for gender there are 12 genders, it believes there really are 12 genders, and it'll use those genders exactly the way they appear in the data. That might be what you want, it might not be what you want, but that's what the algorithms will do. So there are lots of ways we can be fooled. So one way we can be fooled with some algorithms is with outliers. So the definition of an outlier is a data point that is outside of the norm. And I know that's about as specific as I'm going to get. Some people define outliers as 3 standard deviations from the mean or 5, etc., but that assumes the data is distributed in a meaningful way. And it may not be. So we can assess these outliers and look and see what's unusual in the data visually or graphically. The reason why we care is because some algorithms, like linear regression, nearest neighbor, nearest mean, principal component analysis, and to some degree, a little bit neural networks, so neural networks can usually overcome these. Outliers matter. And if you've built a regression model before, you know how much influence an outlier will have in your predictions. Let me just break out of here for a moment and go to KNIME. This is my first time showing some KNIME-isms. This data, this is a very simple workflow, and I'm not doing going into a lot of detail and what I was doing in KNIME. But I'm loading up this data, and I'm just going to right-clicking here to show you how much data I have in this data set. There's about 5,000 examples, and the data set is very simple. We have a target variable called target D and an input variable called last gift. So target D is how much somebody gave in a donation model. This is for a nonprofit, and we're sending out a contact to the donors and asking them to solicit for this nonprofit. Last gift is how much they gave the last time they gave a gift of any kind. So now, if we build just a simple regression model from this using the KNIME regression model node, we can see a very nice, simple little model here where the last gift is a significant predictor, high t-value, and the coefficient is 0.4892. So about half of this last gift feeds into whether or not somebody is likely to, how much they're likely to give the next time. The intercept is about $8. So this is saying that it's $8 plus half of what their last gift was. That's how much we're expecting to give this next time. So very simple, very easily understood. But what happens, and I know Michael shouldn't see this, Rosario, because I put a Java snippet node here, because this is historical. So I don't recommend you using Java snippet nodes. There are other nodes I could have done this with. But if the last gift was equal to 300, I'm going to recode it with 2000. So I'm going to make last gift huge for one of these values. Now let me show you what that does to the data. I'm going to bring in a histogram. We're going to look at before and after. So here's the before. Just execute that and look at it. And here is the, I'm just going to add some more bins. You can see this big chunk for last gift in the lower range and then some small tail. But now that we do this 2000, we're way out of the norm. Let me rerun this. And now we've got this last bucket up to 2000. So that tail gets extended even further. So what does that do to the model? Here's what the model looks like after we rebuild it. And notice last gift, one outlier out of 5,000. And that's the key here. Just one bad data point that is way outside the norm of what we expect. That coefficient changed from 0.5 down to 0.13. And it's significant. But even though it's significant, now much more of the variance of the model is being carried by the intercept. So it's $13 on average, and now we're only adding 13 cents for every last gift dollar. Completely changes the model. So be careful of outliers. Make sure that these outliers are mitigated if you're building models like regression models, k-nearest neighbor, k-mean, those kinds of algorithms. Because squared error metrics, distance-based algorithms like k-nearest neighbor and k-mean are severely impacted by outliers. Okay, missing data. I'm just going to mention very briefly here. We have to be careful with missing data, especially if we are imputing with the mean. And that's a very common imputation method. If you impute with the mean and you have lots of missing data, the key is what it does to the standard deviation. If you've got 10% missing, the standard deviation of this particular variable shrunk from 67 to 64,000, shrunk a little bit. But if there's 30% missing, it's shrinking much more. What's happening is the more data points you throw at the mean, the more missing values that you recode with the mean value, the more the data, the summary statistics of the data make it seem like you've got a more pointy distribution pointed at the mean, and that means that standard deviation calculations will shrink those standard deviation measures down. So any algorithm that cares about distributions, like regression, like k-nearest neighbor, like k-mean, will be severely impacted with because of that mean imputation. So what I usually like to do when I can is, rather than using mean imputation, I usually try to impute with a distribution, a normal random distribution centered on the mean of the actual value. And so if I have to pick a random way or some systematic way to impute missing values, I try to do it with a distribution. I'm going to skip Skew and go to high cardinality because this is another critically important problem that happens with predictive models. So what do I mean by cardinality? Cardinality means the number of levels a variable has. So this applies primarily to to categorical variables. Of course, continuous variables, we expect there to be lots of levels, and we treat them as a number. But for categorical variables, like there's some kind of a code, like a skew. There's lots of skew levels. We would never use it as a number. We use it as a category. Or in the United States, if we're looking at the state, or if you're looking in Europe, you're looking at the country code associated with each customer, you can use those as an input to models. And normally the way they're used as inputs to models is to explode them out using, in KNIME, you'd use the one-to-many node, or you could use some other process to create one column per level. And that means if you started with a variable with 100 levels, then that would create 100 variables. 100 new variables that are 1-0 dummy variables. And that's what is described in the second bullet, that to create lots of these 1-0 dummies. These will tend to be low information content variables. So what does that do to our predictive model? With decision trees in particular, it can cause significant problems. So this is just a simple tree on the right side. This is a cart-style tree. Cart-style trees do binary splits. And when we do binary splits, that means if we've got a variable that has 70 levels, like this RFA3 variable has 70 levels, that means all of these levels have to go either the left side or the right side of our first binary split. The problem will be this. What if some of these levels have only 5 records associated with them, or 3, or 10? These small counts have to go to one side or the other, and the tree algorithm will push them one side or the other based upon their association with the target variable. If you've got 10 examples and 3 of them are associated with your responders, that's a 30% response rate. We assume, or the algorithm assumes, that that's a high response association, and it'll put it on the same side of the split as all the other high associations. Why is that bad? And here's the question. How sure are we, when we see 5 examples or 10 examples, how sure are we that this is a true pattern, or not just some happenstance occurrence? The smaller your counts, the smaller numbers of examples, the less sure we are that it's a true pattern that we're finding and not just found by happenstance. The trees don't think about that. So the trees will overfit and push all of these patterns one side or the other, and we can have a huge problem with overfit. Now in KNIME, this can happen too. One way it happens is if you build a decision tree in KNIME and you don't restrict a binary split, it can create a split for every category, which is very cool, and I like it a lot, except when we have lots of small counts. Like here's a bucket, this N2G value has 27 records. Now this, in the upper right, this is the actual tree that was built, and I'm not going to spare you the pain of looking through every single split in this first split of this tree, but I can assure you there are 70 splits, 70 levels horizontally here. So it's just overfit. So we have to be very careful. So let me go back to my the KNIME workflow again for the high cardinality node to show you that same kind of process. This decision tree node in KNIME, load up the data, partition it to training and testing, and then I created this equal size sampling. Let me just show you this briefly. This equal size sampling node is just doing a stratified sample of our target variable. Our target variable is 95% zeros and 5% ones, so this just made them equal counts. And then our decision tree in KNIME is using target B as our class column. It's using the Gini index to build a cart-style tree, and let's just see what it does. Run this through. And here's that tree that I was showing you just a moment ago, that big Y thing. So why does it matter? Well, if we run this through equal size sampling and then run it on test data. We can look at training data on the first pass and testing data on the second pass by applying the tree, run it through the decision tree predictor, then I'm just sending it through a scorer node. Or let's send it through the raw curve first. Again, this is looking at the testing data results and looking at the raw curve based upon testing data. That's the area of the curve. I really want to see the plot itself. And there's the plot, 0.597. So what did it do from a scoring standpoint? Let me just look at the score node. And we get a 54% correct, 45% incorrect. But on the training data, it was higher. So we had a bit of an overfitting effect with this, with splitting on this one. And this wasn't that severe. There were only 70 levels. If you've got thousands of levels and lots of small counts, you'll overfit more and more and more and cause you some true problems with high cardinality. And so what do you do about it? The way you can handle high cardinality is by binning up those high cardinality variables into a smaller number of buckets. So instead of having 70 levels, maybe you have a dozen or 2 dozen levels. Okay, I'm going to show one other thing while I'm in. Let me go back to 9 and show one other thing. Then we'll open up for the final questions. And I removed the slide from the slide deck. I'll put it back in. But there's one last issue I want to address, and that is one of sampling. We can see the equal size sampling node here that I used for, and I used that for the decision tree just a moment ago. So we run the data through the usual KNIME workflow, loading up from file, do some data preparation, splitting into training and testing subsets. And then with the decision tree, I did an equal size sampling. Here I've got a logistic regression model after the equal size sampling and without the equal size sampling. This could be another webinar unto itself, but one of my pet peeves is exactly this, the equal size sampling idea. Let me assure you that you don't have to do equal size sampling for all algorithms. For the trees in KNIME, you need to do it, but for logistic regression, you don't. So let me do it this way. Let me show you what comes out of this equal size sampling node, and that's from the value counter. In this case, there are 2,425 zeros and 2,425 ones. That means we've got 4,900 and there's equal population sizes of zeros and ones. If I look at the natural distribution of the data, and I alluded to this a moment ago, what the actual distribution looks like, there are 45,000 zeros and 2,425 ones. So that's about 95% zeros and about 5% ones. That's the natural distribution. So the conventional wisdom is that you have to stratify the sample so you don't overrepresent the zeros. And let's look at what model we get from that when we stratify the sample. Here's our model. And this is a classification model. And in the classification model, we get coefficients and we get probabilities out. And we typically like to see this value less than 0.05. And we see a couple of them are not, but that's fine for our purposes right now. Let's look now, if we ran the model without doing the equal size sampling, and I'm not expecting you to memorize this. So what I did was I saved both of these over here to show you the with and without. These are the coefficients with equal size sampling, with stratification. These are the coefficients without. And if you look back at with and without, they're nearly identical in every situation, except for the constant. But the influence of the individual variables, their z-scores, their p-values, and the coefficients are almost the same. For logistic regression, it doesn't matter. Logistic regression automatically adjusts for the relative influence of ones and zeros when the model is built. So you don't have to do your equal size, that's not what I want. You don't have to do your equal size sampling when you're building logistic regression models because the algorithm handles it automatically. Why would it matter? The only reason why I would be concerned about throwing away all the zeros, we started with 45,000 of these zeros, and now we have 2,400 left. That means in order to do the equal size sampling, we threw out 42,000 examples. It might be the case, especially if our 1 is very small, it might be the case that we're throwing away so many zeros that we're not populating the data well enough to build good, stable, predictive models. I don't like throwing away data unless I absolutely have to. So if I do have a situation like this, I'm building logistic regression models. I don't stratify just to make the models quote-unquote work. I throw away data only if there's more data than I truly need to build a stable model. So I think at that is an earful that I've gone through over the last 50 minutes. I'm happy to entertain questions or comments or walk through anything in KNIME or in the slide deck that we've talked about so far.
So hi, Dean, there is a question. If we have data size benchmark that would lower the influence of high cardinality issue.
Is there a benchmark to use? Is there a measure to determine exactly what high cardinality means and when it causes problems? That's a really good question, and I don't have a simple answer for it yet. I use, just as a rule of thumb, I like to see at a minimum dozens of examples per level. And by dozens, I mean like 30, 40, or 50 at a minimum for binary classification problems. Better yet, hundreds. So if I see, so it's not so much the number of levels that kills you, it's the small counts within those levels. So if we have 1,000 levels and every one of those levels has 1,000 records in them, I'm not as concerned from a decision tree model building standpoint. I'd be more concerned from a logistic regression standpoint because that would create 1,000 variables. And that's a different issue with the number of fields going into a model. But just in terms of the effect of the high cardinality itself and the counts, I try to have at least hundreds of examples per level. So sometimes what I'll do to overcome that is take everything with fewer than 100 or 200 records associated with that level, it has bin them all up into the quote-unquote other category. And then that takes care of the problem in a pretty straightforward way.
Okay, there are no more questions. So if you have any questions, please type them in the chat box. Otherwise, we can close the webinar. We are almost close to 1 hour anyway. Okay, so here there is a question. Can KNIME forecast daily basis including seasonalities? For example, Christmas sales, Mother's Day sale, and weekend trend. So time series analytics.
Yes, and the answer is yes. That's really a question of how you set up the data for doing your predictive modeling. So KNIME has a broad framework of nodes that are available to do a wide range of analysis. I'm going to get rid of what I typed in there for the node repository. So in the mining nodes, you can see there's lots of different algorithms that you have available to you here. And I don't know if I brought in the time series analysis nodes in this instance of KNIME that I have right here, but there are specific time series analysis nodes that KNIME has as well. The question really for finding seasonality is representing the data properly in order to identify seasonality. So in the classic time series modeling approach, you would have to have enough lags in your data to go back to capture prior seasons. But the interesting thing to me, and I don't know how deeply we can get into this right now, I can answer some of these questions offline too, but predictive modeling, data mining, arranges the data differently than classic time series analysis. Classic time series analysis has every row is a timestamp and every column is an instance at that timestamp. So if you're looking for, say, sales, and you're trying to identify a seasonality effect of sales, in a column you'd have some measure of sales, whether it's quantity or volume or dollars or profit or something like that for every day. And if you plotted that and you see on the X column you've got date and the Y column you've got that measure, you could see the wiggles in that and identify seasonality effects and apply like an ARMA model or a REMA model or RMAX model to try to identify those trends. Data mining and predictive analytics arranges the data differently. So to do time series analysis using a decision tree or a neural network, you would create delays, time delays in additional columns. So every row would be the measure and every column would be the timestamp. So you would have lots of input and that would just slide down through time. So you would have to explicitly put into your data all the delays, all the taps that you want to identify. So when I do try to identify seasonality when I'm building predictive models, I just need to incorporate a column in the data which either goes back far enough to incorporate the seasonality effect, or sometimes I'll create an explicit indicator, like if we're trying to look at sales on a website and we're trying to identify Christmas season sales, I could have a flag, a 1-0 variable in the data indicating that these sales occurred during the Christmas season and use that to identify the effect of seasonality. So it's all about how you arrange the data.
So one more question is about different statistical packages. If different statistical packages use different algorithms for the same technique.
That's also a good question. There are there's some standard algorithms that all predictive modeling packages have, nearly all of them. And those, the big three are linear regression and logistic regression for linear methods, decision trees in some way, shape, or form, and neural networks. And most of them have at least those three. In KNIME, you have a bunch more that are built in, and you can load up Weka nodes, or you can load up, or you can run R code to increase the number of algorithms. How these algorithms operate are similar but not identical from package to package. So when we were looking at the KNIME decision trees a while ago, you'll notice that in the quality measure, there was Gini index and gain ratio. Those are ways to measure how good a split is. Gini is the measure that the cart style trees use. Gain ratio is the measure that C5 style trees use. There's another kind of tree called the shade tree that uses a chi-square test. So the exact options that you have available in KNIME will be different from those options, the specific options you may have in one of the other tools. So there are some differences, but the basic algorithms are the same. I mean, a neural network is a neural network is a neural network, but you could use backpropagation, you could use RProp, you could use Levenberg-Marquardt. There's a lot of different algorithms people use to have the neural network build and converge. But in KNIME, we use RProp. Another software, you'll have different algorithms. So on the secondary level, there are differences. On the primary level, the algorithms are the same, regardless of what tool you use.
Okay, here I have one more question, and I think this is the last one because then we have to close. Can we run programs in R or Python?
The answer is yes and yes. Now, I don't have a lot of experience doing this myself, and I'll let Rosario comment on it, but there are some new features of running R code in KNIME, in the latest version of KNIME, that makes it it's very easy with syntax checking and also run R inside KNIME. I don't know if you want to run with that, Rosario.
Yeah, so there is a node, there is a full package, an extension package. The package is the R interactive category, and it's available under the KNIME labs. The same, there is a Python, JPython, a few JPython nodes that allow you to edit and run Python code. I'm not very familiar with the Python one, but the R interactive node, if you need help, just send an email to education@knime.com, and also there is on YouTube a video that is a tutorial of the R interactive category. So with all the nodes to read data from R, to build models in R, build R snippets and so on, and do the debugging and everything that is included in these nodes. Okay, so I think we are done. We have no more questions, but the time is also up. So I thank everybody for having participated. I especially thank Dean for having helped with the presentation of this webinar. It was great. And I hope to see you at some more webinars of ours. Thank you. Bye.